like this page a lot. It's really conceptual. So in other words, goes over the concepts pretty well. So that's number 4. Last week, Jordan quickly ran up the stairs. This week, he's hobbling slowly up the same stairs because he pulled a muscle pushing his car. Poor guy. All right. So when does he do more work? The reason that this answer is the same. So in other words, when does he do more work? Last week when he was all good, or the next week when he was playing the tough guy here. So it looks like it should be the same work. The reason that it is because what does work have to do with? So think back to the stair lab that we did. If you've got a set of stairs, and there's pretty awesome stairs. I think they're pretty awesome stairs, but regardless, if he ends up going up these stairs, he's going up this distance. His force, so in other words, his weight of him is actually the force that he is exerting on each one of these steps. So we're assuming if he hasn't really changed weight at all, then he hasn't changed force either. So since work is equal to a force times a distance, has nothing to do with time, doesn't matter. He could take a year to go up these stairs, or he can go up those stairs over the course of a second. Either way, he does the same amount of work. For part B, when does he create more potential energy? Running, hobbling, or the same? Why? Well, let's think about it. Potential energy is equal to a mass times gravity times height. In order to figure out what our potential energy is, we need his mass, right? We can assume that it actually doesn't even matter what his mass is. Gravity, it's 9.8, and the height of the stairs, that doesn't matter either. As long as this mass doesn't change, gravity doesn't change, and height doesn't change, the potential energy won't change either. Well, we can assume his mass isn't changing from the first week to the second week. We can really assume that the height of the stairs isn't going to change. That doesn't make any sense. And even more certain, we can be certain that gravity is going to be the same no matter where we are on the planet, or essentially the same. So that potential energy will not change, because again, it has nothing to do with time. When does he use more kinetic energy? That's a different story, right? Because kinetic energy has to do with mass and velocity squared. So in order to figure out whether or not he uses more kinetic energy running or walking, a pretty good way of asking this question, or a different way of asking this question, is which one does he have more velocity? Well, if I've got more velocity, then my kinetic energy is going to be larger. If I have less velocity, then my kinetic energy is going to be lower. Now, if that doesn't make a whole lot of sense, you can use your math to help you. Let's put in some mock data. Okay. 1/2. Let's just choose his mass to be 10. All right. In reality, it's going to be a lot more than that. Go with 100 if you want to make it a little bit more realistic. That's fine. But it doesn't matter, because what we're going to do is we're going to use two equations here. We're going to say this one is for when he is walking, and we're going to say that the other equation, it's a terrible walking, but the other equation here is running. And we're going to see what happens to our data. Right? The reason I can make up this information right now is because I'm doing it in relation to the problem. When does he use more kinetic energy? Running, hobbling, or the same? Let's take a look at that. All right. So again, we assume that his mass isn't going to change. Right? That wouldn't make too much sense. Now, when he's walking, he's going to have a slower velocity than when he's running. So as long as we have a slower velocity over here and a faster velocity over here, we're doing what the problem's telling us to do, or we're thinking the same way that the problem's asking us to think. So let's say he goes up the stairs 1 meter per second when he's walking. Let's say over here he goes up the stairs at 2 meters per second when he's running. Again, just faster, doesn't matter. These hundreds could be 1 and 1, they could be 10 and 10, they could be 99.2 and 99.2. You can pick anything you want for the mass, just keep it the same, because in real life, that's going to stay the same. This number could be 1 and 2 like we have. It could be 1 and 10 billion. It could be, 0.9 and 1.8. It doesn't matter as long as this velocity is slower and this velocity is faster, because that's what it's asking us. One of them he's hobbling or walking. One of them he's running. All right. So from there, let's go ahead and solve it out. 1/2 times 100 times 1. And it should be 1 squared and 2 squared. Sorry, I missed that. But 1 squared is 1 times 100 is 100 times 1/2 is 50. Well, this 50 actually tells me nothing, right? Because this data was all made up, but it was made up in relation to this other problem. So let's see what's going on over here. 2 squared would be 4 times 100 would be 400 times 1/2 would be 200. This answer doesn't tell me anything either. So you may be thinking, well, what the heck? We made up these numbers, got an answer, it doesn't mean anything. We made up these numbers, got an answer, it doesn't mean anything. Well, kind of, but in relation to one another, this answer compared to this answer, that actually tells us something. It tells us, well, the kinetic energy was low here, but it was higher here. So what happens? Does his kinetic energy change? Yeah, it's a lot bigger when he's running. It's 4 times as much when he's running. When he doubles his speed, if he quadrupled his speed, then we have a different ratio. But regardless, the answer would still be the same. It would still be when he's running, his kinetic energy is faster. So in comparison, these two numbers tell us something. Individually, they tell us nothing. All right, when does he use more power? We could do something similar again, where we set up a couple of formulas and say, well, here's walking, here's running, or hobbling and running, whatever they call it. Walking and hobbling are the same thing, right? I mean, hobbling is just sort of walking with style, but we're looking for power. Work over time. Powers work over time. And again, well, right now we know that time is part of the formula, so obviously his power is going to change, right? Because now we're dealing with something that deals with time. When he's walking, he's taking more time. When he's running, he's taking less time to go up the stairs. All right. So again, we could do something similar to up here and just say, I don't know what his power is, but I'm gonna say his work is 2, his time is 1. On this side of things, we're going to say the work stays the same, right? Because work's not going to change no matter how fast you're going. We know that from above. But this time we'll say that his time is less, 0.5 seconds. So 2 divided by 1 gives me 2. Again, this answer tells me nothing by itself. 2 divided by 0.5 gives me 4. That answer by itself tells me nothing, but again, it's in comparison, this answer to this answer. Oh, it looks like he generated more power when running, less power than when he was walking. All right, part E. If he hobbles up at half the speed that he used to run, how does that change his kinetic energy? And it is a quarter, but let's take a look at that with one of these before-after scenarios. All right, so talking about kinetic energy, so Ke equals 1/2 mv squared. I'm going to do this twice to help me think through it. You might be able to think through it without actually going through and doing all the math, and that's cool too. As long as you realize, oh, this is a squared relationship, you probably can figure out that it's 1/4, but let's see why. Just let's use the math to help us out. That's one of the things that I really hope you get out of this class is, if I'm having some sort of problem reasoning through something, let's go back to a formula and have the formula actually help me. That's such an important thing to be able to do. There's not too many people that are able to do that on the fly, which is great if you can do it. Just shows that you're a real logical thinker. All right, so let's see what happens. All right, it tells us that he hobbles up at half the speed that he used to run. All right, so here's hobbling on this side. Here is running. Okay, so let's say his mass could be anything. Heck, why not go with 100 just because we did before? Doesn't say anything about his mass changing, so we're not going to change his mass at all. even though we're making up the numbers. I could pick a different mass, but if I picked a different mass here, it would also have to be the same mass over here. These numbers have to be the same because we're assuming his mass doesn't change. All right, hobbles up at half the speed. Well, hobbling is over here, so let's just say that is that's 1 meter per second. Running is 2 meters per second, because that would be twice as much as when he was hobbling. And actually, I just realized I picked the same numbers as above. That's okay though. I'm going to end up with a kinetic energy of 50. Over here, a kinetic energy of 200. Now, it's asking us for the relationship between the two. How does that change his kinetic energy? Well, it looks like, oh, it changes it by 150, right? But no, we're looking for how many times does it change it. So if it asked us for how does it change if he's running, well, it would be 4 times as much kinetic energy running. On the reverse side of things, it would be 4 times less, or 1/4 as much kinetic energy. And that's how we end up with this answer. We'll look at this this next one. A pulley system is used to lift a 2-ton heavy thing. You can see we're really getting creative at this point. It's 1,800 kilograms, and I would agree that it is a heavy thing. For every 3 meters the rope is pulled, the 2-ton heavy thing moves 0.6 meters. Calculate the force used. So, all right, let's see what we've got going on here. First of all, we're looking for the force used, and we're moving an object a distance. So I know that I'm going to be dealing with work equals force times distance. All right, so can I figure out anything from this? Well, I don't know my work, so I can't really do that. Ooh, I don't know my force either, so this seems like it's starting to become an issue. Do I know anything about my distance? 3 meters, the rope is pulled, a 2-ton heavy thing moves 0.6 meters. So I've got meters here and meters here. All right, so it may be hard to figure out which one I'm using at this point. So maybe we don't quite fill in D yet. For some of you that feel like you're okay with this, realize that we are the ones that are pulling the rope. So we're the ones that are doing this work. And if you remember back to simple machines, maybe in junior high or something like that, just realize that anytime we're using a pulley, it's not completely efficient. So we might pull it for a much further away than we actually lift something. That's the trade-off. It's easier for us to lift something with a pulley, maybe impossible without. It's easier for us to lift it, but we still got to do the same amount of work. We trade off for it in terms of the distance that we have to move something, the distance that we have to pull the rope. So our distance will actually be 3 meters here, because that's what's going to be associated with the work that we actually do to have to lift this object. All right. If you didn't catch that, no big deal. Let's take another look at how else we could do this. And plus, we haven't even finished solving the problem yet anyway. We need to we see that we're lifting something. So we know that we're going to be dealing with potential energy because we're going to be lifting something a height. All right, we also know its mass. So let's see, does that help us at all? It does. I know the mass is 1,800. I know gravity. Gravity's 9.8 meters per second. Again, the reason that meters per second squared, the reason that I don't have the negative here is because energy is not going to be negative. So if I did have the negative here, I just have to get rid of it in the end anyway. So it doesn't make a whole lot of sense to use it to begin with then. Now my height. Okay, if we didn't catch that this was 3 over here, let's look at this again. For every 3 meters the rope is pulled, the 2-ton heavy thing moves 0.6 meters. So this heavy thing is moving 0.6 meters up. So that's why we're dealing with our height there, 0.6 meters. And when we go to multiply this all out, we'll end up with 1,800 times 9.8 times 0.6. Throw that into the calculator, you end up with 105 584. So 10,584 joules. That's of my potential energy. It's really tempting to stop at this point because it's like, well, it looks like I finished the problem. I'm done with my math, but keep going back to the problem. Remember, especially from the clay lab, remember, ask yourself every single time, what does this unit represent? What does this number mean to me? So what this number means to me is that, first of all, it's in joules, so it represents energy. Force and energy are not the same. The other way we can look at this, so well, it's 10,584 joules to lift of energy to get that object up there. That's how much energy we need. But again, it's not force. So what does this number actually do for me? Well, remember, in order to lift an object up to get its potential energy at the top to be, this number, I must have had to do the same amount of work to lift it up. So I had to do 10,584 joules of work to get it up there. Now I can figure out my forces because I'm the one that's actually pulling the rope, so I'm the one that's doing that work. So this is the distance that I'm dealing with. Well, in order to get F by itself, at this point the math becomes easy, but to get to this point where the math is sort of simple towards the end, it takes a lot of other more complex math. So now it's just 10,584 divided by 3, and I end up figuring out what my force is from there. I think it was 3,000 something. Actually, let me erase this so that we can see what the final answer was. 3,528 newtons. Oh, look at that. I was almost right on top of Miss Mardoin's writing. All right, cool. The last problem we're actually not going to deal with. It talks about the efficiency of a pulley system. We have not talked about the efficiency of a pulley system, and we are actually not going to be talking about the efficiency of a pulley system, so you can cross that one out.